Hi guys, I'm going to try to keep this video somewhat short so we can keep it into one video rather than breaking it up. This will be your first introduction to rational functions. Okay, so by the end of this you'll just have an idea of what rational functions look like and what we mean when we ask if it has an asymptote. So we're starting off with a problem. You're maintaining an average speed of 65 miles per hour. How long will it take you to make a 200-mile trip? Okay, so what we're doing in this number 2 is we're varying the speed. Okay, we're saying if you go this speed, how long is it going to take you? And we're changing that. So if we fill this in, if I go 20 miles per hour, that whole trip, remember the 200 is staying, my d is going to stay 200 for all of these, okay, my distance. If I go 30 miles per hour, then this is going to take me 6.7. Okay, each time I'm just doing this right here. Time equals distance over rate. If I speed up to 40 miles per hour, it will take me 5 hours. Okay, if I speed up to 60, it will take me 3.3 repeating hours. Oops, I missed one in there. Sorry about that. I was one ahead. Okay. If I go 50 miles per hour, it will take me 4 hours. 60 miles per hour will take me 3.3 repeating hours. If I go 70, which I think in this case we are saying is already speeding, it takes me 2.86 hours. And if I go 80, it will take me 2.5 hours. Okay, so write the equation that defines the travel time in terms of the speed. So my travel time is going to be, we're keeping the distance set, so that's why I'm going to put it in 200 over whatever rate that I go. So what happens as we increased our r, what happened to our time? So we can see as the rate increases, the time obviously decreases, but not by the same amount. Meaning if I, speed up 10 miles per hour, that's not going to take that much time off my time. Okay, so they're not going at the same rate. Okay, so now during a winter storm, okay, you have to reduce your speed, so now you're going even less for your 200-mile trip. So let's say I go 10 miles per hour. It's going to take us 20 hours for that trip. And 7 miles per hour, 28.6. 5 miles per hour is going to take 40. 3 miles per hour, 66.7 or 0.6 repeating. Again, we're just doing 200 over r. Oops. That's my time. If I go 2 miles per hour, it's going to take me 100 hours. And 1 mile per hour is going to take me 200. So we're kind of looking at what happens to our time as r kind of goes all the way from 1. And then the other problem we were doing was all the way to 80. Okay, so as the average speed gets closer to 0, what happens to the travel time? Okay, so once this is getting smaller and smaller, if you look at my time is increasing without any boundaries. It keeps going higher and higher. So as the rate gets closer to 0, and you'll see what happens on the graph for this. The time increases without any boundaries. It's just going to keep going up. As I keep going closer and closer to 0 for my r, my time's just going to keep going up without any boundaries. I mean, it's really going off to infinity. So can 0 be an input? Okay, so no, for many reasons actually. For one, if we look at our equation, no, because if I took my 200 over r and I made it 200 over 0, this is undefined. So that's our first reason that we can't use that as an input. Our second reason would be that we couldn't go 0 miles per hour. We can get very close to it, so we can use anything just above 0, but we can't use 0 because it doesn't work in the equation and because it wouldn't practically make sense anyway. So what is our practical domain? Well, our practical domain is, I'm going to put 0 as my endpoint, but watch, I'm not going to put an equal to. My rate can be anything over 0, and I'm going to use 65 miles per hour just because that was the speed limit. We know it can go higher, but we're talking legally. So I actually already did the graph just to save some time. So I took the points. I actually did kind of a rough sketch with my rate on my x-axis, my time on my y, and you see here as my rate gets larger and larger and larger, it goes off this way I'm talking about. You know, we're over here in my graph, my rate's getting larger and larger and my time's going down to 0, but won't actually equal 0. And as I'm up here, my rate's getting closer to 0, and look at my time is just going off without any bounds. Okay, so it's going off to infinity. So what are the intercepts? Okay, so this graph right here is never going to cross the x-axis or the y, so there are no horizontal or vertical intercepts. Okay, so describe the relationship between the horizontal axis and the graph. So as the input increases, or as R increases, okay, the time gets close to 0, but doesn't reach it. Okay, that's what we call an asymptote. It's a line, it could be vertical or horizontal, and you'll see that this graph has two. Where the graph approaches, okay, so that's right here, the graph is approaching it, but never actually gets to it, and rational functions have these. Okay, no other graph that we've looked at so far has these asymptotes. Okay. So describe the relationship between the vertical axis as R gets close to 0. So as R gets close to 0, the time goes off to infinity. That's where we just kind of wrote that same thing on the other slide, but we said it increases without bounds. Same thing. So that's what happens for a vertical asymptote. Okay, this has a vertical asymptote because x is not allowed to be 0, because that makes the function undefined. So the vertical asymptote happens wherever there's a value that you're not allowed to put. And these happen because rational functions are fractions, and so fractions can't have a 0 in the denominator. Okay, so use our graph to approximate the average speed. Oops, I skipped one slide. I'm going to actually not go back to it right now, because if I do, I think it's going to end up overriding the recording. So I'm just going to talk you through the other one. So if you look at number 10, use the graph to approximate the average speed of the 200-mile trip. Okay, so if I do that, if I look at my graph and I have an a time of 5, my rate is about 40 miles per hour. Okay, so I'm actually just going to skip around a little bit. I'll show you those graphs for that other one in a second. So if you look at number 12, okay, using the table and the graphs in problem 11, answer each of the following questions. So what happens to the y values as the x values increase in magnitude without bound? Okay, so the y values get closer. So if my x's are going off to infinity, going all the way to the right or all the way to the left on these pictures, then the y values get closer to 0. They don't actually become 0, but they get close to 0. So that makes that a horizontal asymptote. If x is increasing, going off to infinity, and my y's are approaching 0, but never equaling it, so that means that the line y equals 0, which happens to be the same thing as the x-axis. Okay, the graph has a horizontal asymptote there. So what happens to the y values as the positive x values get closer to 0? Okay, so as my x values get closer to 0, okay, my y values go to infinity. They shoot off without bounds. And the same thing happens now from the other side. What happens to the y values as the negative x gets closer to 0? So if we go from the other side on these graphs, then this same thing happens. The y values go to negative infinity. So I'm going to write that like this. So let me just give it a little sketch, because I'm not positive I'm going to be able to go back to that other graph. We'll give it a try, but I don't want to ruin the video or cut out any part. So all three of these graphs, that F, G, and H from the other side, look like this. Okay, they're just going at different rates, but they all have the same shape, like that. Okay, and so what we're saying here is as x gets closer to 0 this way, well, actually I'm going to, as x gets closer to 0 from that way, it shoots up to infinity. But as x gets closer to 0 from this direction, it shoots down to negative infinity. So that's what I'm talking about in C and D. So from both sides, the graph, when my x gets closer to 0, I shoot off to infinity. So that shows that that's a vertical asymptote. And that would be at the line x equals 0, which happens to be the y-axis. As we change values in these functions, my vertical intercepts, or my vertical asymptotes and horizontal asymptotes also change. Okay, this one's kind of more a really basic rational. So do any of the graphs F, G, and H have intercepts? None of them do. They approach both axes, but they don't actually touch them. Do they have a maximum or minimum? No, because they shoot off to infinity in both directions. Are any of them continuous? And if there's any value you're not allowed to use for x, in this case we were not allowed to use the value, x was not allowed to be 0. If that's the case, it can't be continuous, because it means there's some kind of gap or asymptote or hole at x equals 0. So none of these are not continuous, because they're not defined for all values. Okay, so the last part here I'm going to have you try on your own. Okay, I want you to fill out the table for now the same function with a negative. It's the same function that we did for, I think it was f was just 1 over x. Yes, f of x on the previous page is 1 over x. And I want you to see what happens if you do negative 1 over x. And you'll start to see some reflections. Okay, so then when you do your graphs, make sure you see some kind of reflection happening here between f of x, which is our original 1 over x, and then you're going to end up looking at q of x, which is negative 1 over x. So I want you to make sure when you do that, that you see some kind of reflection. Okay, and see how you do with that. You're just filling in the table and then giving a quick sketch. Okay, so I put another copy of this slide in the back, so hopefully that doesn't kind of interrupt the video. This is the one I kind of skipped before. So if you just want to take a look, I took each of these three functions. Okay, I made a table for each one just to show the difference of the functions. Okay, so you can stop the video and just do the table for that. And if you graph each one, I color-coded them so you can see the difference in each graph. They're all the same shape, but some of the graphs are kind of increasing and decreasing a little bit faster depending on that number.